Hi, today's topic is free space management. We are talking about the way the malloc and free function libc handles the heap operation. The process address space, there are heap region. This is consecutive address region in the process address space. And we are using malloc and free to allocate and deallocate chunks of memory from heap. And they are defined in libc. And I'm going to explain details of how these algorithms works. Let me first explain how we get allocated chunks of memory. Let's look at the 30 byte heap. Their starting address is 0 and ending address is 30. And from the location from 10 bytes to 20 bytes, it is being used. There are two free memory chunks of 10 bytes each. And these two free memory chunks is represented by the linked list. There is free list, and there is head pointer, and there are two nodes in the list. First list, its address is 10, and its length is 10 byte. Second node, its starting address is 20, and length is 10. And then, of course, there is no pointer. From this state, we are going to allocate a certain chunks. Let's say we are allocating 1 byte request. And in the current situation, there are two nodes in the free list, starting from 0, length of 10 bytes, and starting from 20 bytes, length of 10 bytes. There are two nodes. And the way to allocate 1 byte to the user is, for example, carve out 1 byte from this 10 byte chunk, and then return it to the user. As a result, the second node, the starting address becomes 21, and the length is 9. If a user requests memory that is bigger than any of the free chunk size, then the list won't be able to find any such free chunks. However, if there are two small size chunks, let's say this is 10 and this is 10, and these are somehow consecutive, then these two chunks can be coalesced together with the size of 20. Coalescing is merging two free chunks and returning a size of big chunks. If the addresses of them are nearby, we can merge the two chunks. Let's look at this example. There are three nodes in the system. All are length 10, 10, and 10. The first node starts at address 10. The second node starts at address 0. And the third node starts at address 20. If we coalesce these three chunks, then all these chunks can be merged into single large free chunks of length 30. This is what we call coalescing. Okay, so let's think about the syntax of free. When we get allocated a size of 20 bytes and we save it, the address of the allocated memory chunks to the PTR, when we want to release the memory pointed by PTR, we just call free PTR. And we do not pass the size of the memory chunks we want to deallocate. However, somehow the libc library identifies the location and size of the memory chunks it needs to free. We are going to look at the details of how that can be done. The interface to free does not take a size parameter. Then how does the library know the size of the memory region that will be back into free list? Because every memory chunks has a header used by malloc library, malloc function. So when we allocate 20 bytes, actually the 20 plus header portion is allocated to the user. So for example, if this is 8 byte, then even though user has requested 20 byte and the malloc library returns the 20 bytes to the user, that memory chunks occupies 28 bytes, which is 20 bytes plus 8 bytes header. And this header contains the size of the memory chunks. Let's look at the details. This is the data structure for the header. It contains a size and some signature to check whether the given memory chunk is corrupt or not. So every memory chunk that is allocated to the user is preceded by 8-byte header. This is 4-byte. Let's say this is 4-byte. Okay. So if the pointer points to the start address of the memory chunk that has been allocated to the user, then what we could easily guess is PTR minus 8 will contain the size of the memory chunk it needs to free. So in the body of free, actually the starting address of the free memory chunk it needs to free starts not from the PTR, but from the PTR minus the size of the header. So this is how the free function identifies the size of the chunks it needs to free. And what is the data structure for the nodes in the free list? In the previous slide, we saw that there is memory chunk, and this is used by the user. And then this 8-byte contains the size and the matching number. This is the used node. When it is entered, when the node is inserted in the free list, then the matching number is changed to the pointer that points to the next free node in the system. So it becomes a pointer to the node. Let's look at the example. This is how we initialize the heaps. Assume that we have allocated chunks of memory from the operating system to the heap, and we'd like to use the given chunk as a heap. And so there is mf function, and we have requested 4096. It's 4 kilobyte. And then a process has allocated a big chunk, which is 4096 byte, which is 4 kilobyte for the heap. So we are going to embed the data structure to this memory chunk. For example, first, all 4 kilobytes is free because it has not been used by any user process. So the actual size of the heap is the 4096 minus the size of the header. It corresponds to the size of the free nodes. So this size is 4088. This is the size of the header. And because this is the only node in the free list, the next field contains null. So next thing is the allocation. When a user process asks for a memory chunk using malloc, calloc, or realloc, the library will first have to find a chunk that is large enough to accommodate the request. And then the library will split the large memory into chunks and then shrink the size of the free chunks in the list. Of course, there is a minimum granularity. For example, if an application asks for like 14 byte, then malloc library defines certain minimum granularity it wants to return the memory in units. For example, for some system, minimum granularity is 8 byte. So it returns the multiples of 8 byte, 8 byte, 16 byte, or 24 byte. So even though the user requests 14 bytes, it will return the size of memory chunks of 16. For some machine, the minimum memory chunks can be 16. So in that case, that libc library will return the value of memory chunks size of 16, 32, or 48, etc., etc. Let's provide an example. We are calling malloc of 100 byte. Then, in actuality, 108 bytes is going to be returned to the user. So from this state, we have one node, and which size is 4088 bytes. And then after allocating the process to the user, it will contain 3980 bytes. This is the size of the remaining free nodes. And then 100 bytes is allocated to the user. And then malloc function returns the starting address of this memory chunk. Now, let's keep doing the few things. So this is a location. We have allocated first 100 byte, and then another 100 byte, and another 100 byte. So we have allocated 3 100 bytes memory space in total. So the total memory consumed by the 3 pieces of memory allocation going to be 3 times 108. And then it's 324. So out of 4088, we are using the remaining pieces of the 4088, which corresponds to 3764. So this is the chunks of memory in the free list. Still, there is only one node in the free list of 3764 byte. Now, we are going to free one of the memory chunks that has been allocated to the user. Let's say this pointer SPTR points to the second memory chunk that has been allocated to user. Let's call free SPTR. Then let's see what's going to happen. This is the memory chunk that has been allocated to the user, and SPTR points to the starting address of memory chunks. Now we are calling SPTR free. Then there is a single big node. Before freeing the SPTR, there is a single one node of 3764 of size. However, after freeing SPTR, then there is going to be 2 nodes, like this. This is 3764, and the first node is 100. This one used to point it by SPTR. Now it is added to the free list. Okay, so from this part is still being used, and this portion is still being allocated to the user. However, now there are 2 pieces of memory that are being free. First one is the one of size 100 byte. The second one is 3764 byte. Okay, so let's free another one. Now, let's assume that SPTR is pointing to the first node in the system, and then now we are calling free SPTR, and then there's going to be 3 nodes in the free memory list. First one is the one pointed by SPTR, and then it points to the next node in the list, and then it points to the third one. So at the beginning, there are 2 nodes. Continued from the previous slides, there are 2 nodes. First one is size 100, and second one is 3764. Now we are calling free of SPTR, and then now we have inserted another new free node of size 100, and then there is 100, and then there's node of 3764 bytes node. Of course, here the pointer fields point to the starting address of the next memory chunk. So this one contains 16K, and this one points to the value of starting address of the next memory chunk here. This is how the free works. Sometimes, let's say we have freed the last one, and then in reality all the memory chunks are now free, but so far they are free, but they are freed as a separate memory chunk. So instead of there being a free large K memory chunk, there are 4 nodes. First one is 100, second one is 100, third one is 100, and fourth one is 13764 in its size. So if if there comes a request of, for example, 38 malloc, then there is no way for the system to serve this memory chunk, even though it sums up to the 4088 byte. So it should be able to accommodate 1300 byte memory chunk, but because they are segregated, they cannot satisfy the given request. To resolve this situation, libc occasionally merges the adjacent free blocks. That's what they call coalescing. So here, we can coalesce these blocks and make it free larger blocks. That's what we do in coalescing. Let me explain what is going to happen if we call free on the already free mode, freed memory chunk. This is free list. This is head, and let's assume there are two nodes in the free list. If you want to free the certain memory chunk pointed by PTR, and then you call PTR free PTR, then the actual code of PTR sets the next pointer of PTR points to what the head has been pointing to. This is first step. And the next step, update head to point to what the PTR has been pointing to. So this is second step. So as a result of calling free of PTR, the node that has been pointed by PTR will be added to the free list. But let's say this node is pointed by PTR2. So PTR2 stands for the starting address of a already freed chunk. And somehow, we don't know what the reason is, but somehow the application calls free PTR2. If that is the case, then first, the next pointer field of PTR2 will update it to point to what head has been pointing to. So this list will be cut, and then next pointer will point to whatever it has been pointing to. And then head will be updated to the PTR2 has been pointing to. So head remains the same. Now, whatever there was, all the nodes in the field list that is next, that has been following the PTR2, are going to be not accessible anymore. So the field list will be it's corrupt. So please be cautious about not to call free on the already free node. What if we are running out of free space on the heap? Most allocated start with a small size heap. Once it's run out of the space, then application asks for libc, called malloc, to ask for more space to libc, and if libc finds that there is lack of free space in its heap, then it asks the operating system to give him more memory space. In that situation, the set break or break system call is used. Remember that these are our system calls. Again, be reminded that malloc it's a libc function. It's not system call. It's a library function defined in libc. So let's say this is current heap, and somehow you are running out of the heap, and then application asks for libc for more memory space, and libc finds that there is no free space in the heap, then it asks the operating system more memory. In that situation, it calls set breakpoint. So the breakpoint is the term that represents endpoint of the heap. Set breakpoint is a system call that asks the operating system to move the breakpoint of the heap somewhere, and it is used when extending the heap. So by calling breakpoint, if the operating system allows, then heap size can grow like this. So this is how you grow the heap. There are two approaches in managing the free space. First one is best fit, and second one is worst fit. And in best fit, the malloc operation scans the free list and then finds the free chunks that are bigger than the request, but it returns one of the smallest chunks in the group of candidates. The second one in worst fit, it finds the largest free chunks and allocates the amount of the request. The problem of both approach is that in both approach they have to scan all the nodes in the list. So time to find the nodes for that fits a given request is quite substantial. The problem with best fit is that because it selects the smallest chunks that satisfies a given request, the remaining parts can be very small and that cannot be allocated to any of the requests. So in best fit, it creates lots and lots of external fragmentation. So worst fit is the approach to fix the problem that has been arising in the best fit, because it keeps the remaining chunks as large as possible. The problem of worst fit and best fit is its scanning overhead. To avoid the scanning overhead, they propose two types of strategies, that is first fit and the next fit. First fit just returns the whatever first chunk it has come by and it satisfies the given request. The problem with first fit is that searches start always from the beginning of the list. So there are going to be lots of fragment at the beginning of the list. So instead of starting the search always from the beginning, next fit starts searching the list right next to the node that has been allocated. That's next fit. So let's say there are three nodes. This is size 10 and size 30 and size 20. And we need to allocate the request size of 15. Then in case best fit, it searches the entire list and then it selects the node with size 20 and shrink it to 5 and returns the 15 node size node. In case of worst fit, it selects the largest node, which is 30, and then shrink it to 15 and returns the remaining part to the node. Next approach is segregate list. The problem of linked list approaches is time to scan the list. Whatever it is, best fit, first fit, or even first fit, it has to scan the list and find the right nodes to satisfy the request. The other approach is to expedite the search time is segregated list. Let's provide an example of McCusick curls allocator. It has been used by 4.3 Unix. The idea is very simple. An operating system maintains an array of same size node. So there are 5 pointers here, first pointer, second pointer, and fifth pointer. So these are array of 5 pointers, and each pointer points to the head of the list of size 32, 64, 128, 256, and 512. So if you look at the actual layout of the memory, then these are allocated chunks. These are all allocated. So for example, this one is allocated chunk and the size is 64. And this is allocated chunks of size 32. And this is 32. So this is 64. The node of this size is 32, and this size is 32, and this is size of 512. Okay, so it points to the allocated chunks. And then for each head, this head all contains to the field list of the same node of same size node of 32. And this one is the same size node of 64. And there are nodes, all the nodes in this list are size of 128. So here, because kernel maintains a list of pointers, each of which points to the same size node, the time to allocate a free list, time to find the free list is very easy and fast. But of course, in this approach, there are internal fragmentation issue. Internal fragmentation, because if the application requests for 64 byte, then it allocates 128 bytes node. Nearly 50% of the entire nodes are unused. So this is McCusick-Curls allocator. We call it a segregate list. There is an issue in segregate list. The problem is how much memory should we dedicate to each list. what is the right ratio between the memory chunks that has been allocated for the free list in each size list. That is a big issue. One of the most famous memory allocation algorithm is Buddy system. In Buddy system, it creates the small buffers by repeatedly halving a large buffer, and it coalesces the J free buffers. When a buffer is split, each half is called the buddy of the other. The minimum size is 32 bytes, and Buddy system allocates a bitmap array to monitor each 32-byte chunk of the block being used or not. Let me provide a detailed step on allocating chunks. We are going to allocate 4 chunks. First one is 156 byte. Second, third, fourth one corresponds to 128, 64, and again 128. Now we are going to allocate 3 memory chunks in a row. The size of them are 256, 128, and 64 byte. First, there are 1 free chunks of 1024 byte. We cut into half and make it as A and A prime. The size of memory chunk A and A prime is 512. So we have to split it again. We have to split A into B and B prime. And then size of B is going to be 256. So we are going to allocate memory chunk B for the request of allocating 256 byte memory chunk. And then we are going to serve the allocate request for 128 byte. B prime is 256 byte. So we have to split it into 2 of C and C prime, and we allocate C to the allocate 128 byte request. So this is served. And then there are a memory chunk request for 64 byte, and this is C prime is 128 byte. So we split it into 2 and then make it as a 64 byte each, and then allocate D to the third memory request. And of course we have to update the bitmap accordingly. And next, we are going to allocate 120 byte memory chunk again. In the previous slide, there were 2 memory chunks, one with 64 byte and one with A prime, which is 512. Now we have to serve the 120 byte memory chunk request from the A prime. So we split into 2 and make it as E and E prime. And then E is 256 byte large, so we have to split into 2 with 120 byte each, and with F and F prime. And then as a result of splitting the 2, we are going to allocate F to the request. So on the free list, there are 3 nodes. One node is 64 byte, the other node is 128 byte, and the third one is 256 byte. So each of them are pointed by the appropriate head pointer list from the array. And of course, we have to update the bitmap accordingly. Now we are going to free or release the memory chunk. First, let's release the C. C is 120 byte. So after releasing the C, we have to update the appropriate bitmap, and then let the pointer to the 120 byte free chunk list points to C. And then because there was, in the previous list, there was 120 byte pointer has been pointing to the F. Now we are inserting C to the head of the list, and then let the next pointer of C point to the CF prime. Now let's release D. D was 64 byte. Let me just briefly go to the previous page and what happens if the D is released. Here, D are being used. So if D is released, then D can be coalesced with D with its buddy D prime, form a memory chunk of 128 byte. And then it becomes C prime, and if the C prime becomes free, then C prime and its buddy, the chunk C, becomes free, so they can be coalesced together. So due to this recursive coalescing, releasing the chunk D creates a big large chunk of size 120 byte. So it is going to be inserted into the free chunk list of size 128. And so, 256. So the pointer that has been pointing to E prime is updated to B prime, and next pointer of B prime will point to E prime. So this is last configuration of releasing D. As you can see, there is an issue. If a small chunk needs to be allocated, then there is going to be lots of splits. And also in the small chunk are returned, there is going to be a lots of coalesce. So in some cases, some algorithm postpones splitting and merging the request. Let's analyze the characteristics of the algorithm. It causes the internal fragmentation because it only returns 2 power of 2 size memory chunk. But it is very easy to find body and so easy to perform coalesce. It is good. It does a good job of coalescing adjacent free buffers, and it is easy to exchange the memory between the allocator and paging system. But because of the frequent split and coalesce, the performance may degrade. And the release routine needs both the address and size of the buffer, and the partial release is not sufficient. So this is the disadvantage of buddy system. Slab allocator is an advanced form of the segregate list. A slab is a set of kernel pages. It consists of the same object, such as inode, locks, and sockets. They are all initialized before it is allocated. Using an object in the kernel consists of largely 5 phases. First one, it allocates memory chunk, and it initializes the various fields of the object. It then uses it. After finish using it, it deconstructs it, and then return it to the kernel. Out of these 5 steps, constructing the objects takes a substantial amount of time. So an engineer has proposed to populate a slab with same size and same type of object, such as inode. And after a process finishes using the inode, instead of completely returning to the kernel, it proposed to reuse it for later usage. That is slab allocator. Let us summarize what we have covered in this class. We have learned how libc algorithm manages heap address space. They are using a linked list. And then kernel provides 2 types of memory management algorithm. First one is buddy, and that is used to allocate the memory to the process. And then another one is slab, and it is used for allocating from memory for the small kernel objects such as proc structure, inode sockets, and etc. This is the end of this class.